Hello, everyone. Welcome. I'm Wendy Liu from the University of Toronto, Canada. Thank you for joining us today for the fourth annual virtual conference celebrating the International Day of Women Statistics and Data Science. This year's theme is Thriving in Your Environment. We are recording the event, and the videos will be available on the CWS YouTube channel. We kindly ask you to post your questions to the speakers using the Q&A or the chat. Okay, without further ado, I am delighted to start our session, S407, Analysis of Data from Complex Systems. This session features three speakers from Canada, all from Wilfrid Laurier University. Unfortunately, Julia, the second speaker, won't be able to join us, but fortunately, Professor Zilin Wang will be able to present the talk on Julia's behalf. Okay, so are you all ready? So our first speaker is Ipseeta. I'm going to unshare first. All right. All right, so I'm turning over to you. Ipseeta, would you like to try share your slides?
Yes. Is my screen visible?
Yes. If you can make it full screen, that would be great.
Yes. And is that all right?
Yeah. Great. Thank you.
Thank you. Can I start? Sorry.
Yes, please do.
All right. Good evening, everyone. My name is Ipseeta, and my research, which I'm going to be talking about today, entails developing a framework to analyze time to event outcomes from non-probability samples. And Professor Zilin Wang, who's here in our talk today, is one of my supervisors. Now, large longitudinal health cohorts like the Canadian Partnership for Tomorrow project or the UK Biobank often recruit participants via volunteers or clinics or specific health networks. This type of non-random sampling technique is known as a non-probability sample, where members do not have a known or equal chance of being included in the sample. These samples also enable the inclusion of many variables and because they're less expensive and faster to conduct, but they also introduce selection bias. This leads to the samples being not representative of the population unless adjusted. Not just that, since the members of the population do not have a known chance of being included in the case of a non-probability sample, a classical design-based inference approach isn't directly applicable because it assumes that the inclusion probabilities are known. This is where the use of an auxiliary probability sample comes in. In a probability sample, every member of the population has a known non-zero chance of being included because the sampling is conducted in a random fashion. Now, this randomness enables the inferences obtained from a probability sample to be generalizable to the population. Because these probability samples are more expensive and time-consuming to conduct, sometimes we have to rely on the existing probability samples to gain the information we need. Now, these surveys might not, although include the information, the accurate outcome information that we need, but they more often than not include important covariate information on variables such as age, sex, smoking status, etc. Now, the covariate information from a probability sample, the covariate distributions of such covariates are representative of the population. And we can use this auxiliary information to estimate the inclusion probabilities for a non-probability sample using a logistic regression model. Now, let's assume we have a non-probability sample A and a probability sample B, and the parameter we're interested in estimating is the population mean. Now, if we fit a logistic regression model for inclusion probabilities, then we can estimate the inclusion probabilities for the non-probability sample, which once that is done, we can then for every unit in the non-probability sample, give each unit a weight, which will be the inverse of these estimated inclusion probabilities. We then have a re-weighted non-probability sample whose covariate distributions are now representative of the population. Now, to estimate the population mean, we're interested in three main estimators, the first of which is the inverse probability weighted estimator, where we weight the sample outcomes from the non-probability sample with the inverse of the estimated inclusion probabilities to get rid of the selection bias. Now, if the inclusion model that was used to estimate these inclusion probabilities was correctly specified, then the inverse probability weighted estimator will yield unbiased estimates of the population mean. The second one is the outcome regression estimator, which for which we use the non-probability sample to fit an outcome regression model to get the predicted survival outcomes, or in this case, to get the predicted outcome values for the probability sample, which when weighted with the survey weights provides the outcome regression estimator. And the last one is the doubly robust estimator, which was proposed by Chanley and Wu, which combines an IPW estimator and an outcome regression estimator, such that if at least one of the two, the outcome regression model or the inclusion model, is correctly specified, then the doubly robust estimator will yield unbiased and consistent estimates of the population mean. Now, we can directly apply these previously discussed methods to time-to-event analysis, and we'll see why in the slides to come. But first, let's introduce you to what the time-to-event data consists of. It has three main components. The first one being the time until the event of interest occurs, TI star, the predictors, which might affect the occurrence of the event, and the status variable, which is an indicator variable which takes the value of 0 if the event happened at that time, and the value of 1 if the observation was censored at that time. Now, censoring refers to the scenario where we have been following up with an individual since the beginning of the study, but we don't know whether the event that we're interested in occurred to them or not, either because they were lost to follow-up, or they withdrew from the study midway, or the event of interest just did not happen to them until the end of the study. Now, instead of looking at time until the event happened, we will use TI, which is the follow-up time. It is the amount of time a person is tracked in a study, either until the time the event happens or until the time they were censored, whichever happens first. Now, let's look at the example on the right and consider a clinical study, which is where we're tracking the time until the progression of liver disease after treatment. And the black dots on the left mark the start of the study, and the X's show the disease progressing at a particular point in time, and the O's denote the patient being censored at a particular point in time. Now we can see that patient 1 was followed up with for 7 years, and at 7 years, until 7 years, they did not experience disease progression, and after that, they were censored. Now, patients 2, 5, and 6 can be seen that they experienced progression in years 6, 2, and 4, respectively, and patients 3 and 4 were censored at time 6 and 5. Now, the parameter we're interested in estimating is the population survival probability at time t. The survival probability, also known as the survival function, is the probability of lasting past time t. The graph on the right shows the estimated survival function for time to disease progression from a non-probability sample. That's the curve in purple, assuming that the curve in blue shows the true survival probabilities for reference. And we can see that without adjustment, survival curves from a non-probability samples may be severely biased, and correcting for this is essential if generalizing to the population. Now, to be able to use the previously discussed estimators, it is assumed that the outcome variable is fully observed. But in time-to-event analysis, the outcome t is not always fully observed due to censoring. And we can't simply use censoring times because they're not true values, they're partial information. This is where we adopt methods that can handle censored data effectively. And first of which is the weighted Kaplan-Meier estimator. It is a non-parametric estimator and a function of the inverse probability weighted estimator. that helps estimate the survival function under independent censoring. The weights are the same as before, which was the inverse of the estimated inclusion probabilities. And if the inclusion model used to estimate these inclusion probabilities is correctly specified, then the weighted Kaplan-Meier estimator will yield unbiased estimates of the survival function while handling censor data. A drawback, however, of this estimator is that it does not account for covariates. The next technique we're interested in is the Cox proportional hazards model. It helps provide a generalization of the outcome regression model, outcome regression estimator, where the outcome now is survival probability. The Cox model is a semi-parametric model used to fit the hazard function, which is the probability of instantaneous death. From a fitted Cox model, we can compute survival probabilities, which, when combined with survey weights, helps us get the regression estimator. Now, if the Cox model is correctly specified, then this regression estimator will yield unbiased estimates of the true survival probability. We propose a doubly robust estimator that can be adapted in time-to-event data, where we often have censored data. This estimator is made up of 3 components, the first one being the weighted Kaplan-Meier estimator, and the third term is the outcome regression estimator that we just talked about. The second term helps take care of the bias in case of model misspecification. Now let's look at a very important property of our proposed doubly robust estimator. If let's assume the inclusion model is correctly specified, but the outcome model is misspecified, then the weighted Kaplan-Meier estimator will yield unbiased and consistent estimates. The third term, however, they will introduce bias. But because both the second and the third term are trying to estimate the same population survival function, their difference cancels out asymptotically. Now, if it's the other way around, if the outcome model is correctly specified, but the inclusion model is misspecified, then the outcome regression estimator will yield, will be design consistent and will yield unbiased estimates of the survival probability. However, the first 2 terms, because they form the mean of residuals, they will converge to 0. Thus, the most important property of our proposed doubly robust estimator is that if at least one of the 2, the outcome model or the inclusion model, is correctly specified, then our proposed doubly robust estimator will yield design-consistent estimates of the true survival probability. Now, before we move on to the simulation results, let me quickly introduce you to the simulation setup. So we simulated a finite population of size 20,000 with survival time and status variable and covariance xi, from which we were able to calculate the true survival probability. From this population, we took a non-probability sample of size 500 with known event times and covariates. We also took an auxiliary probability sample of size 1000 containing common covariates as sample A, but unknown event times. Now, the first case, which is the true case where we can say that both the outcome regression model and the inclusion model are correctly specified, we can see that the line in orange, which is the doubly robust estimator, is completely overlapping the true survival probability, which is supposed to be the line in blue, which we can barely see. Now, looking at case 2, which is a false true case, where let's assume that the outcome regression model is misspecified, but the inclusion model is correctly specified. And here we can see that the regression estimator, the line in green, is clearly biased. However, our doubly robust estimator, the line in orange is still very close to the population survival curve, thus giving us design consistent estimates. Case 3, which is the other way around, where now the outcome regression model is correctly specified, but the inclusion model is misspecified. Now our IPW estimator, or in this case, the weighted Kaplan-Meier estimator, the line in red, yields biased results. However, our doubly robust estimator still holds strong and gives unbiased and design consistent estimates of the true survival probability. And the last case, which is the worst case scenario, where both the outcome regression model and the inclusion model are misspecified. In that case, since all the information we have is incorrect, all the estimators fail. Now, what we're working on currently is in developing a variance estimator for the proposed doubly robust survival probability estimator. And we're currently trying to get bootstrap variance estimators for the same. For the future, we're looking to apply our estimator to real-world surveys where we want to use the Ontario Health Study for our non-probability cohort and a CCHS for our auxiliary probability sample. Here's a list of the references that is relevant to my presentation today. And thank you for listening.
Great, thank you. Our next speaker should be Julia, but Zilin is presenting on her behalf. So, Zilin.
Sorry, let me sorry. How do you share? Ah, right there. I'm sorry. It's long day. Okay. Can you guys see my slides well? Is that in full?
Yes.
Okay.
No, not a full screen. If you can make it full screen, that would be great.
Okay. Sorry, where do I get the full screen? No.
Usually the view.
Yes.
Great.
Good.
Thank you. Yep.
Okay. Hi, everyone. Sorry, I'm my student Julia is not feeling well, so I will give the talk on her behalf. Okay, so what Julia, this is her undergraduate thesis, so I hope get more feedback. So we want to actually send out to some applied publication. Okay, so the topic of this project is actually try to figure out what college stats of the basketball players can actually result to a success drafting. And then the case we're curious about is on the WNBA Women National Basketball Association games. Then we're going to use 3 methods, models to analyze the data and then get some sense of what stats are important when we're looking at the drafting of the players. And so the objective, the outline of this talk, of course, I'll give the objective, I will describe the data, and then I also will briefly introduce the methodology we use, then give a discussion, and then some further for the research. Okay, so talent selection lies at the heart of team sports. The WNBA is one of the most competitive sports league. And then most WNBA players, they also play in college, and now their things are recorded by this National Collegiate Athletic Association. And now just try describe a little bit the structure of the NCAA is that within the NCAA, they also divide the teams into conferences. So to actually each level of the competition in the conference are actually quite comparable, which means the conference between conferences actually have certain level of difference. Okay, so that's just worthwhile mentioning so later on for our modeling. So the objective for this is the project aimed to apply statistical method to identify the key characteristic of successful WNBA draftees. So what do I mean? We mean here is that we want to look at the college stats of player and then to see whether the draft will be a success or not. Okay. And now what we hope is that we can actually use the model to predict the success of the drafting. And now then we also ask ourselves another question, a little bit from a long-term angle is what factor contribute to their ability to sustain the longevity of their career in WNBA. Okay, so that's actually the question that we ask ourselves, and then we try to find which model actually is suitable. Okay, so the data is actually hand assembled by Julia. Actually, it was her thesis, undergraduate thesis. What she did is she combined both the WNBA season data with the NCAA data that the players, their career actually doing their college. And then so they did, she did this school anything before 2004. Okay, so it's actually quite a hard job to get this data set ready. Then also in the data, there's one important variable is the conferences. Now, originally there are 21 college conferences, but because there are some conferences are very small and there are only a few team players actually get drafted into the WNBA game. So that's why we're actually crashing some to create some like combine all the college in one conference to compare with the rest. Okay, so that's how our data look like. Okay, so how are we going to answer the question? So what was the question? The question is what college stats actually suggest we can actually have a success drafting or not. So now then that gives us the question, so what do you mean by a success drafting? So some summary statistic we checked is that the average number of games a player can do within a season is around 30 games. So that's why we said, there we go, let's use 30 as our benchmark. So if the player played more than 30 plus games, then we will say, okay, our draft is a success. If not, then it might not be. Okay, so that would be our response variable and will be the success of the drafting. Now, this response variable will be used in the two models I list up there, the logistic regression model and the logistic mixed effect model. The first model only take into the individual effect, and whereas the second model will also look into the clustering due to the conferences. And then we also apply our data to a Cox proportional model to check the longevity of the players in WNBA games. Okay, so that's the model. We also look into a whole bunch of covariates and something that I'm not very familiar with, but Julia is very good at this. So basically we want to looking into is their self-performance on when playing, whether they help others, so that's the assist, whether they make a mistake, and those are things with a foul. And also when we're talking about basketball, height is always something noticed. We want to see whether height can actually make them more successful in their career. Okay, so those are the covariates that we're going to use. So the first model, it's a logistic regression, just the same as usual assumptions. Okay, and I should talk a little bit more about how we define our response variable, which I had already talked earlier. And then, feeding all this, the variables I mentioned earlier, and this is the final model that we use if we do use logistic regression to predict or to see the association between the college stats to the success of WNBA games. And then what we notice is that only 4 survive. Now 4 variables are significant in this case. And then the foul actually, again, will negatively correlated to our success. That's actually understandable. And now that I want to draw attention is assist. So what assist is that is whether the player also help the teammates to score. Okay, so in this case, the assist is actually significant. So, and then Julia gave some discussion here. So total point, total assist is positively related to our probability of the benchmark, whereas the field goal and then the foul is negative. Then the total rebound is not significant. Okay, so that's the thing. And please make a mental notes about the assist, because later on we will see that variable again. Okay, so now the second model we use is actually for to take into account the clustering among the conferences, so that we borrow this logistic mix effect model. And now, sorry, it's still a lot. So the same covariate we use for logistic regression is also in here. Then we try the random intercept model, where the delta J is the one to represent the conference effect. And now then this is the result of our mixed effect model. What we notice here is that we have again, similar type of significant parameters. Okay, and now assist again survive. Then this time we notice the height of the player finally is significant in this logistic regression in mixed effect model. Okay, so that's the height, total field goal made, and total assist. They all positively related to the probability of the benchmark. Then the personal foul is going to play a bad negative relation to the to our probability, and then total rebound again is not going to be significant in this case. Sorry. Okay, so that's the result for the two models, where we're looking at basically is not kind of short term. We call short term is that we just see whether I get this person in the game, whether he or she will be successful or not. So we then look into the longevity using the Cox proportional hazard model. And everybody here are all in survival analysis. So here, what we're looking at is the risk. What we want to see is what kind of college stats actually create risk to actually shorten the career path of our players. And then our model, same thing being, this is actually quite interesting. So what we notice is that the result shows several things. First of all, the effect of what we saw as so-called short-term effect is now still there. They do have some kind of risk, okay, cost risk, but it's quite minimal. But height and the interaction term between height and position, you can see give us a big shock there, like a giant risk, okay? So the result will be the total cell in college are related to the low hazard rate. And then the assist, which the one that helping people are still play a very important role to the person's career, of course. And now the last one, it's actually making lots of sense, is that top players are at high risk for career termination, which is known that top players tend to injure more often, more easily. So that's why I think this model we fit here actually gave us more confirmation of that the myth seeing taller, even though they can get in easily, but it might leave the career much earlier than relatively shorter players. Okay, so that's the three model. And now what do we come from here? The most important factor, the scoring opportunity for teammates assist is very important factor for drafting. Efficient shooting, that's the PTS 3P, that's also very important. Free throw line and interaction between, and then we also talk about the height, and height is always something related to mark a basket player, but in some sense for their career, maybe they need to take care of themselves so that they can keep the career length. Okay, so that's all. I think I try make our 15 minutes, and thank you very much.
Great. Thank you, Zilin.
Okay.
Maybe you can start another set of slides. I have a question, but I'll wait till the end if we have time.
You know, this is 21 years of teaching. I think I can do it. Okay. Just wait, sorry. Oops. Okay. 1 second.
If you can make a full screen, it'd be great.
Yes, I'm trying. So
Great,
good.
thank you. Yep, so great.
Okay. Okay. Hello again. Okay, so in this project, I want to talk about a work I've been working with Mary Thompson from University of Waterloo, modeling missing data for complex surveys. Okay, so to start the talk, okay, I want to first give a few empirical motivations to kind of motivate why we come up with the research and then the model we're using. Okay, so we all know complex survey or survey itself, and it has been used in many aspects of society. So in 1994, the Canadian Alcohol and Drug Survey, there's a question asked, have you ever used and tried cannabis? And so in this table down here is saying that what we can notice is there are 200 people actually either refuse or pretend don't know anything about that particular question. Then time moves on when we move to 2019, and the same question was asked again. Then we realized there's a zero non-response. So everybody happily answered the question. Now, we are people from not from Canada, just there's some insight is that in 2018, Canadian government legalized the cannabis, so that afterwards, so this question basically saying is whether people answer question or not, or the non-response rate, it actually relate how they feel about that question. So that's the first empirical example I want to talk about. Now, in the second one, it's some evidence from some economics research. So what they notice is that the wage and income level of the participant actually positively correlate to the non-response when analyzed. This is evidence from Canadian Survey of Labor and Income Dynamics. So what this one basically saying is whether I answer the question or not actually depends on how much my income level. Okay, so that's one of the evidence. So the third evidence I want to mention is from the clinical trial. So some in the reference at least there, what they find is that the patient's severity also relate to the non-response rate, which also makes sense. For example, if you ask the day, how are you feeling? If the person is not feeling well, maybe either they can answer or they actually cannot describe the things very well. Okay, so all these three simple empirical examples back some kind of challenge that we want to tackle on. So what this challenge is, the arbitrary of the survey questions are related to the response rate or non-response rate of particular questions. Also, as we're talking about the income level, the severity of the disease, and then which suggests the value of the variable of interest also decide the chance of whether people will answer the question or not. Okay, so that's the two things that discovered from that empirical examples. Then we also feel this is a quite important way is because in when people handling missing values, if you're doing just experimental data, that's okay just to delete. But when we survey sampling, each sampling unit all attached to a sampling weight, which is a representation of the population. So in a analyzed survey, this missing value is actually quite important, and we shouldn't should take care. We shouldn't ignore. And then also, what do we know is that if we kind of leave the non-response away alone, not to take care of it, and the estimate will give us a non-response bias. Also, the variance may be inflated. Now, given the nature of the three questions or the challenge, the phenomenon that we're looking at is the mechanism of the in-item non-response called the missing not at random. Okay, because it's related to, so this slides just for people are not familiar with the terminology I use, I just try to introduce two things that we're going to use again. So when we're talking about item non-response, we typically talking about two types of variables. The first is the study variable of interest. So that's the variable we want to know about. And unfortunately, they're missing values. And then sometimes if we're lucky, we have something called the baseline variables. And in those variables, there's no missing observations. And then the study relate to the missingness of we call that is called propensity score, which is the probability of the study variable being non-missing. And now there are two types of mechanisms. The first one is most commonly used, and then lots of research has been put on, is called missing at random. This case is saying that the propensity score, so the probability of non-missing, only depends on the baseline variable. So we need to find that baseline variable. And then there's another one, is called missing not at random, which is very relevant to the empirical example I mentioned earlier. It's in this case, the probability of non-missing actually depends on both on the study response and the baseline variables. Okay, so that's the variable. So how what we want to do then is to add a little bit of contribution to the non-missing not at random. Now, how are we going to think about this question here? So what we think is that when we're looking at the previous questions, seem to us the value of the study variables are deciding whether the person will will give the non-response or not. Okay, so then we say, okay, how about let's divide the support of our random variable. Let's break them in pieces. And now within each piece, within each subset, we're going to check the missing probability, the probability being missing. Okay, so that's the non-homogeneous nature of people's behavior, whether answer the question or not, is the core of this, the model building. Okay. So, so the proposal framework, and then again, we have our study variable. Remember there, I don't have a baseline, which is a good thing. Okay, we don't need other information, just a study variable. In the variable, we have parameter of interest data there. And then we start breaking up our support of our random variables in B subsets, non-overlapping subsets. Then we are saying, okay, within the J's subset of my support, the probability of missing or not missing, they're different. So we stand for by the PJ there. Okay, so that would be the probability of not missing if I'm in the domain J or in the subset J. Then we also realize, remember we say about it's difficult to looking at every piece. We actually see, okay, now I have my study variable. Which domain does this variable actually belong to? So if I'm looking at my random sample, I say, okay, there's a probability of my random variable belong to the certain domain DJ. We call that QJ, okay. And now, so that's the part of the new thing we add. Then we have the second part, which is quite standard, saying, okay, now I'm looking at my whole random sample. I might take 1 or 0. If it's a 1, my Y is now missing, and 0 if it's missing. So this ballooning distribution with the probability of success to be A. Now A here is actually 1. 1 minus A will give us our propensity score that the the mechanism of the item non-response tend to look. Now, if we're looking at our probability of missing, Y be missing, we can say that both the probability of missing in each subset, as well as where this random variable value is, that QJ there, I'll take into account. Okay, so that's the part. And afterwards, things just the usual thing, and we're going to use set up our likelihood function. And then the likelihood function is actually very neat in one way of, when I first time saw this, I was very impressed. Okay, is that normally, I mean, when we teach students about likelihood function, we have the sample data, then we set up the likelihood function. But in here, we actually give part of the likelihood function to the things that might be missing. So that's in the middle of the formula there, that L0I. So that's actually saying that's the likelihood contributed by the value, and the value of my study variable might be missing. Okay, so that's the very neat part. And now the second part of the likelihood function is just the usual one. We got our data, we can set up our likelihood function. Okay, so that's the two parts of my likelihood function. My time is good. And then finally, I have, I'm talking about survey sample. In order to get survey sample, we need actually have the weights. Okay, so this is pretty standard. So my sample is from a finite population. Now each unit in the population will have something called the inclusion probability, and then the reciprocal of that inclusion probability will be my weights that I have to use to do my estimation. Okay, so lots of theory has been developed in this type. So in particular, this pseudo likelihood and estimating equation by Binder, Skinner, Godambi, and Thompson give us very nice score functions going through the optimization procedure. Eventually, we're able to estimate our parameter of the study variable, which is actually that's the objective. We also will get our the missing probability within each subset. Now, based on that missing probability, we can also get our propensity score. Okay, so that's the three nice things we have. Now, the asymptotics variance estimate has already been established. So just want to show you some result. Very limited simulation result has shown that the relative bias for all three variables are pretty low. Okay, so that's so that's a percentage. So that's one. I also did the variance estimates. I don't have time to show, so I didn't. So very quickly. So finally, I applied this method to the data to look at the depressive symptoms, which we believe that might give some kind of the missing out at random, because different severity of depression may give us different type of non-response. Then this is our result. Then we can see that when people have very severe depression, the proportion of missing actually can go very high. Okay, sorry about that. Okay, so everything I think take into account the non-homogeneity of our support of the study variable. We solve all the inferential problems. And then we also don't need the baseline variable. and then estimation is not very tedious. The adaptability may be a problem, maybe not. I have to do a little bit more investigation. Okay, thank you very much for that. I'm sorry, I may go a little bit.
No, that's okay. I know it's very difficult to have all that put all together in 15 minutes. And so I'd like to conclude the session by thanking the two great speakers for 3 wonderful presentations. And thank you everyone for joining us for this session. And with that, I'd like to encourage all of you to explore other sessions that are still ongoing and then enjoy the rest of the conference. Okay, thank you everybody.